Last time, I reviewed some concepts from linear algebra and defined our first group, which was the group I called GLN of R, which is a set of all invertible n by n matrices A with entries Aij in the real numbers. You could also, there are other groups you could do if you didn't want to work with vector spaces over the real numbers. You could also define a group GLNC, which would be the same thing where the entries of the matrix were complex numbers. Or you could define the group GLNQ. This is complex numbers. This are the field of rational numbers. Same thing where the entries are rational numbers. We'll start with the real numbers. And let's remember, first of all, what a group is. So having defined this, we showed that it was a group. And a group is, by definition, G is by definition 1, a set with a product structure. So by that means if you have two elements in the set, A and B are in the group, then you get a new element, A dot B, the product of A and B, which is a new element in the group. So there has to be a product. And the second thing is the product must be associative. That's the most important thing to check. Namely, A times B times C has to always equal A times B times C. That's a tricky property. Once you have this associativity, then the product of any n elements in the group is well defined, independent of the order that you take the product. Once you have associativity for 3 elements, you have it for more than 3 elements. And the second condition is the existence of an identity, which I'll denote E, which has the property that the product of any element with the identity, the product of the identity element with is A. So every element, no matter how you product it with the identity, gives you itself. And the fourth condition is the existence of inverses. And that means that for every element there's an inverse, which denoted A inverse in the group, with the property that no matter how you multiply A by A inverse in either order, you get back to the identity. Those are the properties that characterize a group. Rather simple properties. And we saw that the matrices, which were invertible, formed a group under matrix multiplication. Associativity is rather difficult to check from the definition of matrix multiplication, but if you think of matrices as representing linear operators and multiplication being composition of linear operators, then it's clear that the composition of 3 operators is the same no matter how you compose them. The identity element is the identity matrix with all 1s on the diagonal and 0s elsewhere. And the inverse element is the inverse matrix, and that's why we have to assume that we only took invertible matrices here.